Hokie dokie. The time is now 4 p.m. We're going to be doing 1025 Quiz 9 review session starting now. This session or this quiz is a lot about critical points or critical values, and those are the x values for which f, the original function, could possibly have a max or a min. And then it's a lot about where different functions have maximums and minimums. We're going to be doing a lot of things by hand and a lot of things by Excel. So about half by hand, about half by Excel. Okay, so let's get started. Number one, find the critical points of this function. So to find the critical points means to find the x values for which f prime of x is equal to 0. And then in other situations that you don't have to worry about, it's also the x values for which f prime of x does not exist. But we will just think about it as where f prime is equal to 0. So the first step is to find the derivative and then set it equal to 0, and then we will solve for x. So first derivative of this function, we take the derivative of the numerator terms and then just leave any numerical denominators as they are. So 3x squared over 3 minus 14x over 2 plus 6. So if you need to review power rule for the derivatives, feel free, but I'm not gonna review that for you. That's all we did there. So 3 divided by 3 leaves us with just x squared. 14 over 7, we're left with just minus 7x, and then plus 6. So we set this derivative equal to 0, and our goal is to solve for x. And once we solve for x, we will have our critical points. And in order to solve for x in this situation, we do want to factor. So we want two numbers that multiply to 6 but add to negative 7. It's usually easiest to think about two numbers that multiply to the 6 first. So the only possible option, no, take that back, sorry, 6 is not prime. So one possible option would be, say, 2 times 3. 2 times 3 in no capacity could add up to negative 7, so we use 6 and 1. And then the question is, how could 1 times 6 give us 6, but also give us negative 7 when we add the 2? Oh, sorry, I meant to do 6 and 1. I have 6 and 6, don't I? I'm trying to multitask and write too many things at once. How could 6 and 1 multiply to 6, but add to negative 7? And that's only if both of those are negative. So x minus 6, x minus 1, negative 6 minus 1 is negative 7, and negative 6 times negative 1 is 6. So anyway, each of these factors we set equal to 0, and then we solve for x. So we get 6, and we get 1. If it's easier to think about, you just get the opposite of what it looks like. Like if it looked like negative 6 and negative 1, we get positive 6 and positive 1 as our x values, which make f prime equal to 0, therefore as our critical points. And that's it. So set f prime equal to 0, solve for x by factoring. Number 2. And I mentioned it towards the very start, but something I did not mention in this problem was because these are the x values for which f prime is equal to 0, in other words, because these x values were the critical points, these are the possible locations for where f, the original function, has a max or a min. Okay? So now in this one, they say which of the following points does the function have a maximum or a minimum? So it's asking the same thing, just in a different way. So this is just like asking for the critical points. So the process will be the exact same, except the derivative and factoring process, or solving for x process, will be a little bit different. To take the derivative of this function, we need to use the product rule. If we have an a times a b, then f prime will be a prime times b plus a times b prime. A prime, the derivative of e to the 2x, would be 2e to the 2x. That uses a small chain rule portion. So if you need to review chain rule, feel free, but really this is like the only chain rule you'll have. Basically just e to the 2x has a derivative of e to the 2x, but then the derivative of the inside, the 2x, is also 2. So we have to pull out a 2 in addition to the e to the 2x. I hope that makes sense. B is just 3x plus 4. A is just e to the 2x, and b prime is just 3. The derivative of 3x plus 4 is just 3. So we want to also set this equal to 0. I'm going to get rid of this. And we want to factor now. So factoring will look different in the sense that we want to pull out a greatest common factor in this case. So the greatest common factor will typically just be the e term. So we're going to factor that out. So we'll get e to the 2x. And when we take away the e to the 2x from this big term, it'll leave us with 2 times 3x plus 4. And then when we take out e to the 2x from this big term, it'll leave us with just a plus 3. So we pull out e from both big term groupings. And then the idea is this. We have this factor, e to the 2x, and then we have this big factor, 2 times 3x plus 4 plus 3. In order for all of this to be equal to 0, we ask ourselves, could it come from this? Could it come from the e to the 2x? Are there any x values for which e to the 2x could be equal to 0? Could this ever equal 0? No. And the idea is, because e to the 2x can never equal 0, because e to the 2x or e to the x has a horizontal asymptote, so it never hits 0. Because there are no x values for which e to the 2x equals 0, if all of f prime is ever going to equal 0, it's not going to be because of the e to the 2x. It's going to be because of this right factor, the 2 times 3x plus 4 plus 3. So what we're going to do is set that equal to 0 and solve for x using algebra. So we just set this stuff equal to 0 and solve for x. So factor, or distribute, I mean. So 2 times 3 is 6, and then x plus 8 plus 3 equals 0. 8 plus 3 is 11. Subtract 11. Divide by 6. We get that x is equal to negative 11 over 6. And that is our critical point. In other words, the x value for which f could have a max or a min. And that's the idea. And that'll be the same general process every single time. So we want to use the product rule. And then you set the derivative equal to 0. Factor out the e term, and then just set the other stuff, the non-e factor, equal to 0. And solve for x. Number 3. How we doing? Any questions in here? Of course not. That's great. Love to see it. All right. Number 3. For the function f, whose derivative is given in the graph, which of the following statements is correct? So we're given f prime on the graph, and they're asking about where f has maximums and minimums. So it's very important to mention that, kind of like we've seen in the last couple of problems, f will have possible maximums or minimums wherever the derivative is equal to 0, because that's what we've been doing, right? We've been finding the derivative and setting it equal to 0 to find critical points, in other words, where f prime is equal to 0, where f could possibly have maxes and mins. So what I'm hinting at here is, if they give us the graph of f prime, then f prime is equal to 0 at these x-intercepts, okay? And so it's at these x-intercepts for which f prime is equal to 0, also for which f could have a possible max or a min or a max. And what I've gone ahead and done is label the maximums and minimums. And let's talk about why they are maximums and minimums in this case. All right. Wherever f prime, this function is f prime, wherever f prime changes from positive to negative, in other words, around like 2.5 right there, right? that's where f has a maximum. Because if f prime is changing from positive to negative, that means that f is changing from a positive slope to a negative slope, and that indicates a maximum. Color code that in green here. We'll do max. And then likewise, wherever f prime, this graph, changes from negative to positive, or below to above the x-axis, f will have a minimum. So I've done a lot of over-explaining. The biggest thing I would remember for this one is that your maximums and minimums for f will come from the x-intercepts of the f prime graph here. And so typically when you're answering this specific question, you can kind of just count the number of x-intercepts between the intervals that they give you. So to simplify it, all right, take a good look at that. I'm about to delete it. It's really good stuff, but it's going to distract us from how I'm going to talk about this next stuff. All right. So between 1.3 and 4.3, between 1.3 and 4.3, just count the number of x-intercepts. We just have 1, right? And they say f has no maxes and no mins. So that's a total of 0 maxes, 0 mins. But we have at least 1 max or min. So this is wrong. Between 4.3 and 7.2 would be like there to there, roughly. So again, between those two values, we have just 1 x-intercept. And here they say no maxes, no mins. That's a total of 0 x-intercepts. So that is incorrect as well. Let's go to the next one. 1.3 and 9.7. 1.3 to 9.7, we have all 3 x-intercepts. So they better have a total of 3. 2 maxes and 1 minimum. That's a safe bet. That's a total of 3. 2 plus 1, right? And then let's confirm by eliminating the last one. 4.3 to 9.7. 4.3 to 9.7, we have 2 x-intercepts, but they only have a total of 1 and 0. So 1 plus 0 is 1. It does not in any way equal 2. So C is the only one that makes sense. The total number of x-intercepts between 1.3 and 9.7, equals the 2 maxes and 1 minimum. And again, earlier when I labeled max, min, max, that's also why it's 2 maxes and 1 minimum. All right, lots of explanation for that, but lots of good stuff. Let's keep going. Number 4. For this one, we want to first identify the x values for which f prime is equal to 0. Again, it's always about where f prime is equal to 0 because those x values are the possible locations where f has maxes or mins. So this one would give us 3, this one gives us 1, and this one gives us -3. These are coming straight from these factors. Okay? So then, what I like to do is really just focus on the 1 or the -1, whichever one we get. So when we look at x equals 1, we are looking for the colors that have either maximums or minimums, or maybe just like a kind of flat behavior, like a 0 slope behavior right at x equals 1. So when we look at x equals 1, we can see that green has a positive slope and orange has a negative slope. So those do not have 0 slopes, whereas blue and pink definitely hit those maxes and mins right at 1. So we can narrow it down to blue and pink. And then the next step is plugging in 0 into f prime. You can plug in any value, but plugging in 0 is a really easy number to plug in. We're going to plug in 0 everywhere you see x within f prime here. And all we care about is the sign of f prime at the end. So the first one, 0 minus 3 is negative, 0 minus 1, negative, 0 plus 3, positive. So altogether we have a negative times positive. Whenever we have an even number of negatives, we have 2 negatives, the result is positive. Okay? What does this mean? F prime at 0 equals a positive, which means f, the function we're looking for, has a positive slope. But not just anywhere, right at the x value that we plugged in. So it has a positive slope at x equals 0, which means we're looking for an increasing behavior right at x equals 0. So right at x equals 0 is like right in the middle here. And so between our two remaining options, blue and pink, which one has the positive slope right at x equals 0, that would be pink. So pink is our answer. All right, so focus on the 1 or the -1 that comes from the factors, and then narrow it down to 2 colors, and then plug in x equals 0 to f prime to get the overall sign. And then if f prime is positive at 0, then f has a positive slope at x equals 0. And if you plug in 0 to f prime and you get a negative, then that means f has a negative slope at x equals 0. Let's do one more. So from these factors, again, we just get 2, -1, and -5. Again, I like to go for the -1 or the 1 because it's just something that's like more central. Usually it's all you need is just to look at one value, you know. So when we look at -1, a little harder on the eyes here, but when we look at -1, look closely, we can see that orange has a negative slope, green has a positive slope, so we can eliminate those, and we can see that blue has a max, pink has a min. And so again, we eliminate green and orange. We're left with blue and pink again. So now let's plug in 0 into f prime. And so we get the negative on the outside, and then 0 minus 2, negative, 0 plus 1, positive, 0 plus 5, positive. So as you notice, that negative on the outside really, like, I didn't like make a big deal out of it. It does stay on the outside, and it does affect the overall sign. It kind of just introduces a 4th sign that we do have to incorporate into the overall, you know, multiplication now. So f prime at 0. We have 2 negatives, so again, an even number of negatives results in an overall positive. So again, right at x equals 0, we're looking for a positive slope for f. So between blue and pink, which one has the positive slope? Right in the middle, right at 0, that would be pink. So pink again. All right, that's pretty much it for those ones. Let's keep going. Number 6, they give us f prime as another factored situation, but now they have exponents attached to those factors. So the first step is finding the x values for which f prime is equal to 0. Similar situation, right? 8, 4, and this is a weird one, but if you just have x to some power, 0 is the x value that would make that equal to 0, which would make the overall f prime equal to 0. So 8, 4, and 0, x equals 8, 4, and 0 are the possible x values I guess they are the x values for which f has possible maxes or mins. But sometimes, even if they're x values that make f prime equal to 0, they might not always have a max or a min. And so let's talk about what I mean. If we look at this first factor, and we know that gives us x equals 8, but we notice that its exponent is 6. An even exponent results in no max or min. And we'll talk a little more why in just a moment. But for something like this, x equals 4, or that factor x minus 4 gives us x equals 4, and its exponent is odd, an odd exponent will result in a max or a min. But we can't tell just by looking at it, so we'll have to show what to do in just a moment. But again, this one gives us x equals 0, which has the even exponent of 8, which means no max or min. Okay, so using just this, let's see if we can narrow down or, you know, eliminate some options, and let's see if we can eliminate our options and find the right answer first. So like x equals 8 should not have a max or min. Do they have anything on 8? They say max at 8, so that can't be right. Let's try, there should be a max or min at 4. Okay, that doesn't help us. For 0, there should not be a max or min, so neither a max or min at 0. This says max at 0, that's wrong. This says max at 0, that's wrong. So just by process of elimination, we can actually tell that A is our answer. But what we could not do with the information we gathered so far is tell whether we should have had a max or a min at 4. We could have relied on process of elimination to find A as our answer, so I guess we do have a min at 4. But in this next example, we'll talk about how to actually, analyze whether we do have a max or a min, and I'm going to do it using Excel, something I have not done before on video. So let's talk about it. So you might notice that all these all these exponents are odd, which means we will have a max or a min at every single one of these x values, which means if they say neither max nor min, we can go ahead and eliminate those, I guess. But then between C and D, how are we going to tell if we actually have a max or a min at x equals 4? Because that's the main difference here. Okay, let's break out Excel. So what we're going to do for this one is cover my face up, psych. All right, we're going to input x values so that we can include the x values we are concerned with. So we have what? -1, 4, and 5. So we just want to start a little to the left and finish a little to the right of that. So if our lowest is -1, let's start at like -4 or something. -4, -3, and we'll highlight these and then drag this corner down until we're past our highest one by a few. So we'll go up to like 8, and our highest one was 5. So what we're going to do is actually input this f prime function, okay? So we're going to do equals, in parentheses, we'll do x minus 5. So anywhere you see x, we're doing a1, so a1 minus 5, raised to the 5th, times, in parentheses, a1 minus 4, raised to the 3rd, in parentheses, times, in parentheses, a1 plus 1, raised to the 3rd, and that should be it. All right, so hit enter. It's going to be crazy numbers, don't mind that. Just drag that down, and let's point out a few important things. We notice the zeros right here, here, and here. Okay, I'll be fair, I did not do enough spaces. This is actually a really good example. I'm glad I did this. Let's try something else. What we're going to have to do, this is a very rare case, where we have 4 and 5 right next to each other, like the 4 and the 5, the 0 and the 0. We actually need to plug in values in between 4 and 5 so we can get a better image here. So what I'm going to do is start at -4 still, but I'll go up by 0.5 now. So I'm going to do -3.5, and then -3, and then so on, okay? So I'm going to highlight these, and I'm going to drag this down until we're past 5, right? So I'll go like to that. That should be plenty. So now let me actually get rid of that. And let me drag this function down. All right. So why did I change it? I changed it again because we have x values that are right next to each other for our zeros. So like we had 4 and 5 right next to each other, and we couldn't see what was going on in between them. We couldn't see if the f prime value was positive or negative. So that's why I changed that. So now let me highlight these. So as you might notice, these are our x values, -1, 4, and 5, for which f prime is equal to 0. These are the x values we're concerned with, like whether they have maxes or mins. At -1 here, we can see that the f prime values are changing from negative to 0 to positive, right? So basically just negative to positive is the main concern. Earlier, I probably erased it when I did all that stuff earlier, but earlier I mentioned how a change from negative to positive would lead to a minimum, because if f prime is changing from negative to positive, that means the slope's changing from negative to positive, so we would have a min right at -1. So if we analyze these other ones, at 4, from the left to the right, we see that the sign of f prime is changing from positive to negative, which means we actually have a max, because a change from positive to negative is a change in the slope of f from positive slope to negative slope, so that leads to a max. Whereas number 5, or x equals 5, changes from f at x equals 5, f prime changes from negative to positive, and so naturally there will be a minimum at x equals 5. Okay, so there, scroll back down to where we were. So let's answer our question here. Our main concern was what was happening at x equals 4, and we can see that because f prime changed from positive What the hell is happening? All right. F prime changed from positive to negative from left to right around 4. That means we have a max at 4. So we're looking for C to be our answer here. To address this specific example here, we only really had to check what was going on right at 4. But I did want to do all these values just to show you, like, you could just do it like this if you wanted to. Like from start to finish, just input the X values, input that, and that could also tell you if you don't have a max or min or do have a max or min. What it would look like if you did not have a max or min is like if this sign was negative and this sign was negative. If there was negative to negative and there was no sign change, you would not have a max or a min. If you went from positive to positive, then there's no sign change, so you wouldn't have a max or min. So that's kind of what you look for neither a max nor a min. Hope that makes sense. Let's bring this back up. Bring me over here. All right. Ooh, goodness. Let's check this one out. So use the graph below to identify what's true. So we're given the graph of f of x, and they're asking about 3 local maximums. So let's talk about how they define local maximums real quick. Local maximums are just the highest points relative to areas around them. So like if you put a little box around this thing here, that point that I've pointed out is the highest point within that little box. And same with this little point here. These are local maximums. So on this whole graph, there are only 2 local maximums. So this should say 2 and not 3. So that's false. Number 2, the graph has exactly 1 local minimum. Now, for a local minimum, it's the opposite idea. It has to be the lowest point relative to points around it. But they will also consider not just ones that look like minimums, but really they will also consider endpoints as local minimums. As long as if you put a little box around those points and those points are still the lowest points on the function in that little box, then that will be a local minimum. Okay, so this graph has exactly 3 local minimums by their definition. Okay, I do not agree with their definition, but that's how they will define it. Okay, so 3 local minimums, so that is false. And then they say the global minimum. The global is another word for like absolute minimum, if you're familiar with those. Absolute minimum is the absolute lowest point on this entire function. So the lowest point on this graph is definitely right here. And that is at x equals 4. So they messed up. That should be x equals 4. And in this case, that means none of these are correct. Okay? Bada bang, bada boom. Let's do one more. Sorry, this looks a little crazy. I had to block out some of the excess stuff I had. So number 9, this one says the graph has exactly 0 local maximums. Already false. There's got to be at least 1 local max in this case. Excuse me. Because they will consider this endpoint as a maximum. So this has 1 local max. They say this graph has exactly 1 local min. Oh shoot, you know what? I'm forgetting. Let me back up. They would also consider this as a local max down here. These 2 endpoints would actually both be local maxes. So I apologize. This is 2 local maxes. Then they say this graph has exactly 1 local minimum. And that is actually true. There's only 1 low point on that graph, and that's it. Yeah. So the global max is at x equals 0. Now that might be true. So the absolute max, the global max, is right at the start at x equals 0. So that's actually true, I think. So I'm going with 2 and 3. See how we did. Good work. All right. That was number 9. Let's do a number 10. Great problem, great problem. I've never taught this with Excel, I don't think, on video, but I'm going to do that right now. So we're going to use Excel for this one. So let's demonstrate. I'm going to use a lot of Excel. I'm going to show you how to beat the system and get confident with Excel. Okay. For this one, we are given this function, and they're asking about the values of g, or the y values, at the local maxes and local mins. So what we're going to do is just input x values first. I'm going to go from -10 to 10. That's usually a safe window. And then we're going to input the function right here. Okay, so equals 2x cubed. So anywhere you see x, you're clicking on A1. So 2x cubed plus 6 times a squared, A1 squared, and then minus 48x, 48A1, and then plus 2. That should be it. So we'll click and drag this corner down. So we fill out all those. So we get all our y values. And then if you highlight this, both columns, you insert a scatter plot. We'll do the lines, one with the lines there. We can get a nice little image and see where the max and the min are. So if you wanted to zoom in a little bit, there's a nice convenient way. Once you have this chart made and these are still highlighted, you can actually like change the window here for which values are included and not included. So I'm just gonna start it here and then bring some of these down too. Keep it in like the hundreds. Oh, that's beautiful. Look at that graph. All right, so changing the window, or basically like highlighting different values, will create a different graph, right? So looking at the important parts, the max and the min. The max is right there. If we leave our mouse highlighted over it, it's 162. And that makes sense even when you look at these values here. Look how the y values are changing. They're negative, then they're positive, they're getting larger and larger. They hit 162 and then they start going back down. So the maximum is definitely 162. And so looking at our little answers here, we definitely see a 162 here and here and here. But I guess it wouldn't make sense that the local min and max is 162, right? So that's out of here. So that only leaves A. But let's, talk about why A is right. When we hover our mouse on that minimum there, we see the y value of -54. So that's why our minimum is -54. And we could see that again on the y values over here. The y values are decreasing, 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 decreasing. They hit -54, and then they start increasing, increasing, increasing again. So -54 is the lowest value achieved within this window. It's a local minimum. And that's pretty much it. So, yeah, that's how you do Excel for that one. Let's keep going. Number 11. Another beautiful one we will use Excel for. They ask, what is the global minimum on this window from -2 to 2? So, we just input x values from -2 to 2, just like that, very lightly. And then we're going to input this function they give us. I'm trying to navigate all this stuff, sorry. So just input this function. Wherever you see x, you're going to type A1 or click on A1. So we'll do equals A1 cubed over 3 plus 2 times x squared over 2 minus 2. Yeah, that should do it. And then plus 8/3. Hit enter. Drag this baby down. And they're asking, what is the global minimum of this function on that window? So global minimum means when you look at these y values and you ask yourself which one is the smallest, which one's the lowest y value, -1.33 is our answer. So that is our global minimum. So the global minimum is just the smallest y value you see in this window from -2 to 2. So we ask ourselves which one of these is equal to -1.33. If you want, you could always use Excel to type in each of those answers. Equals 0, equals -8 over 3, equals -4 over 3, equals 2. You get the idea. So these are the A, B, C, and D, and our lowest value is definitely -1.333, and that was option C. So C is our answer. Hey, what's up? How's it going? All right. Hope that makes sense. No questions. Looking great. Let's do number 12, and then honestly, most of the other problems after we do number 12 will be in Excel as well. They're very challenging problems to do by hand, but Excel makes them very easy. So checking out this problem, they give us some information about a fruit tree yield in an orchard containing 100 trees, 264 pounds per tree. Yield is decreasing by 2 pounds per tree. If you wish to maximize the annual yield, what's the total number of trees that should be in the orchard? So here's the process for this one. The first step is setting up the yield function, or the yield equation. The yield equation will be the number of trees multiplied by the pounds per tree. Okay, so let's set that up. The yield will equal the number of trees. The number of trees starts at 100. And they tell us we are not removing any already planted trees, but we are planting additional trees. So the number of trees at any one point is 100 plus t, 100 plus the number of trees we are planting. Pounds per tree, in a similar sense, will start at 264, but they say it's decreasing by 2 pounds per tree, so minus 2 for every additional tree planted. Every additional tree planted is represented by t. So this is our yield equation. All right, sorry, my neck is chronically stiff. I'm always trying to roll it. All right, this is the function that we're finding a max of. This is the yield we want to find a max of. So to find a max of any function, like we were kind of doing at the start of this session, we want to take the derivative of this function and set it equal to 0 and solve for t. So before we do that, I might recommend, so we don't have to do the product rule, I would recommend distributing everything or foiling everything out. So when we do so, we get 26,400 plus 264t minus 200t minus 2t squared. We combine like terms. I might rearrange some things here. We get negative 2t squared plus 64t plus 26,400. Now that we have this in its simplified form, this is our yield. We are finding the max of yield, so we take its derivative to get negative 4t plus 64. We set that equal to 0, and we are going to solve this for t by adding 4t, dividing by 4, and getting that t is equal to 16. Now, what do we do with t equals 16? We plug that in to the number of trees expression, because they are asking for the number of trees in this case. So we take that 16, and to find the total number of trees, we do 100 plus 16, and that would give us 116. Something to mention is that sometimes they ask for pounds per tree. You will know if they're asking for pounds per tree if in the answer choices, instead of trees, it says pounds per tree. The whole process would still be the same, but once we found t equals 16, instead of plugging it in here, you would plug it in here into the pounds per tree. So just to demonstrate, it would be 264 minus 2 times 16, so 264 minus 32. So 232, I think, would be your answer in pounds per tree. So had they asked for pounds per tree here, 232 would have been your answer. But since they asked for trees, we plugged it in here, so we got 116. Hope that makes sense for the two different versions. Let's do more Excel stuff. This is number 13. This is where it starts to pick up. I think I have videos working this one out by hand. I can't remember if I have videos working this out in Excel. So that's what we're going to do today. Assume the size of a tumor. T days after a dose of chemotherapy was administered, given by this. So this represents the size of a tumor. T days after a dose of chemotherapy. If the second dose should be given when the tumor starts to regrow, after how many days should the second dose be given? So the idea is we want to find the minimum of this function. We want to find the minimum of the size of the tumor, because what they did is administered a dose of chemotherapy, which is meant to shrink the size of the tumor. But then they say they're going to administer the second dose right when it starts to regrow, which is right at the location of the minimum, where it's shrinking and then it starts growing again. So we're going to graph this function and find where its minimum is. and it's going to be somewhere in this window. Like these are the t values or the x values, the input values that we're going to plug into Excel. Okay, so let's talk a little bit more about what I mean. So t values go here, and we're ranging anywhere from 2 all the way to 14. So I'll just go ahead and start it right at 1, and then go up by just 1 each time. 7, 8, 9, 10, 11, 12, 13, 14, and we'll go at least 2 more past that, just so 14's included, I suppose. So we're including all these t values. This is how we're looking at these answer choices is guiding which t values we plug in. Okay, now we're just inputting this function that they give us here, and this will tell us the size of the tumor at all these t values. So 0.382 times e, which is exp, so times exp of negative 0.36 times t, or a1, close that, and then add 0.004 times exp of 0.32 times t. All right, close that, drag this baby down. So all these values almost mean nothing. It's so hard to look at decimals like this. So we're going to highlight all of these and go to insert a chart, go to scatter, and just like that we can get a good image of where we're at a minimum here, right? So if I'm riding the function here, we start a little high up and we go down, 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 we hit a minimum, and then we go up, 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 up. That's pretty good, huh? Just thought of that on the spot. So we hit this minimum down here at between 6 and 8, I would say. So is that an answer, between 6 and 8? That is an answer. So that is where the minimum occurs. That is where the size of the tumor is big, and then it's shrinking, it's shrinking, it's shrinking, it's shrinking, it's shrinking, and it hits this minimum size, and then it starts to regrow right there. And so they want to administer the second dose right at that minimum there. Okay, over explaining, but you get the idea. 6 to 8 is when that minimum occurs. So that is our answer. Okay, let's keep going. Call this number 14, and we will also use Excel for this one. Now be very careful with how you use Excel for this one. We need to know how to input the x values here, or the t value, or I guess in this case the h values. So I think, to be honest, I can probably just do like 1 to 10. I think 1 to 10 works for this one. Let's try that. 1, 2, 3. We'll just highlight these. Go to 10. And then we'll just input the function. And okay, so let me explain this one a little bit. To explain this one, they give us a work equation. The work or the total energy a crow uses to break open a whelk when flying at a height of h meters. Okay, so then they say, what is the minimal amount of work? So we're finding a minimum of this function that they can use to open a whelk shell. Okay. Okay, so I'm going to input this function. Wherever we see h, we are just clicking on A1. So big parentheses, whoops, equals, big parentheses, 16.3 divided by h minus 0.76. So in parentheses, h minus 0.76, close parentheses, make sure to add the +1, close the big parentheses, and then multiply by an extra h. Hit enter, drag this down all the way. Actually, for this one, you could probably just scan through these values. So again, these are the W, or the work values. So it's 68, 28, 24, 24, 24, 24, 25, 26. So it hits that 24, and then it starts going back up. So 24 is the minimum amount of work used to break open the whelk shell. Does that make sense? So 24.1 is the lowest work value. That's pretty much it. So just do 1 to 10, input the function. The minimum is the lowest y value. Let's keep going. That was number 14. This is number 15. Now the x values are a lot trickier for this one. So they give us the growth rate of a particular species of fish is modeled by this. X is the number of fish, And they say determine the largest rate for this species, meaning find the maximum of this function. So the number of fish will be extremely large in this case. We want to deal with not like 10, 20, 30, 40. We want to deal with thousands. We're going to start at 0 and go up by 5,000 each time. So 5,000, 10,000. We're getting in the 100,000s here. And to make this fun, we're going to go all the way to this number. This will kind of be a guide. So 400,000 in this case. So we're going to go to 400,000. Went way too far. Let's back it up. So right there, 400,000. Going up by 5,000 each time, starting at 0. So now we will just input this function. 0.04 times x. Wherever we see x, we're clicking on A1. We'll do times, big parentheses, 1 minus x over 400,000. Click and drag this down. Fill out all our values. We get that. We can highlight both columns. We'll get a beautiful graph here. Check this out. Boom. Look at that. So we get this perfect parabola. And the idea is that we have this perfect parabola from 0 all the way to that 400,000. There's a reason that 400,000 is there, because it's always halfway between 0 and 400,000, which we will have our max. And our max is 200,000 comma 4,000. Again, we want to know just what the max rate is, and the max rate is given by the y value in this case. So the 4,000 is the y value, so that is our answer. That's all there is to it. So if you wanted to sort of shortcut this one even faster than how we just did it, it is always the case that halfway between 0 and 400,000, or halfway between 0 and this number here, in other words, just what is half of this number, 200,000, is always the x value where the max occurs. So like if you know half of this value would give us 200,000, and 200,000 is the value where the maximum occurs, you could then just plug in 200,000 to this function. And again, it's at 200,000 that the rate is 4,000. So yeah, I hope that kind of made sense. The shortcut is cut this number in half, plug it into the function, get your answer. Okay, that was number 15. I don't think anyone's in here. Any questions? All right, I think we're good. Oh yeah, I forgot about this one. All right, so that was number 15. Let's do number 16. This is also an Excel one, and then we'll do a couple like statement ones, and we'll wrap it up. So this one in Excel. Let's get rid of these. What we do is we are also going to input t values based on these answer choices here. So between like 35, 45, 45, 55, all the way to 75. Let's just go from like 30 to 80. We'll just go 5 left and right. And we'll go up. Let's just go up by 1. That's probably fine. We'll do 30, 31, 32. And we'll go all the way up to 80. Way too high, way too high. Back it up, back it up. All right. And now, the function we will input, it's very not explained here, but what we do is multiply this function s by this function p, and that will give us this seed production function that they're asking us to find a maximum of. So what we're going to do is when we input a function, we're going to input this function times this function, okay? So equals, big parentheses, negative 0.3 times t squared, so a1 squared, plus 30t, so 30 times a1, plus 0.6, close that off, and we're multiplying this function s by this function p. So in parentheses, we're putting the function p, 50,000, divided by t plus 100. So bam, plus 100, parentheses, hit enter. Crazy number, but keep dragging it down all the way to the 80, and I guess just highlight both columns. Let's see what we were working with here. Go to scatter plot. I feel like I'm super zoomed in, sorry. Okay, so we can kind of see what's going on here. It's going up, 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 up. It's a low max probably between 40 and 50. And then it starts going down. Now the tricky part is it in the early 40s or later 40s? Let's get a closer look, shall we? What we can do is kind of what we did before, where we change our window. So let's only go from like 40 to 50 on the values here. Let's scan this up. So it only goes to like 50, and we scan this down, so we're going 40 to 50. Oh, that didn't help, did it? But I guess that helps us see our answer, because if we go a little tighter, oh, that's beautiful. So play around with it, I guess. We can see that the max is definitely in the early 40s here, and then it starts to go down. Okay, so early 40s, we're looking at between 35 and 45 there. So that's pretty much it. So input t values based on the answer choices. Input the function that is s times p, and then use a scatter plot to find the maximum value. And where the answer will always be the t value where it occurs. So the x values, I guess. Okay. All right, that was number 16. Let's do a few statement ones, and we are going to call it a day. All right, which of the following statements must be true? If f is differentiable and the first derivative changes from positive to negative at c, then f has a local minimum. So if the first derivative changes from positive to negative, that means that the slope of f is changing from positive to negative. Now, when the slope changes from positive to negative, does that look like a local minimum? No. Hopefully it looks like a maximum. So when the first derivative changes from positive to negative, we're talking about f has a max. So, false. Number 2, local extrema cannot occur at the endpoint of a graph. Originally, I would say that is true, but I think by their definition, it will be true, because we saw that earlier. We saw those graphs that would do something like this, and so the graph would look like this, and I would say that this is a minimum and this is a minimum, and those are known as endpoints. And so those were local minimums on the endpoints, so local extrema can occur at endpoints. Oh wait, so I have it backwards, sorry. The wording's always confused. So they say local extrema cannot occur at endpoints, so they would say that's false. Okay, sorry, had to talk through it. A global max is also a local max. That is not true. It is sometimes true, but not always. But you know what? Based on their definition, oh, good night. I always forget how they do this one. I'm pretty sure they would say that is true. A global max would also be a local max. But maybe by their definition, a local max is not always a global max. Got that? Global max, I think, is a local max based on their definition, because anything that's a high up point is still going to be a local max, regardless of if it's an endpoint. Okay? Yeah, I think that's true by their definition. All right. So then number 4, if f is differentiable, meaning you can find the derivative and the first derivative changes from negative to positive, then it has a local max. That's the opposite of number 1, I think. So negative to positive, negative slope to positive slope, local max, that's false, because that would be a local min. So we'll write that up here. F has a min. So there's your maxes and mins right there. Number 5, if f is differentiable and changes from falling to rising, now we're talking, falling to rising, f has a local minimum. That is true. Falling to rising definitely has a local minimum right at, C, or the bottom there. So hopefully, fingers crossed, we're going 3 and 5. Nice, all right. Good deal, good deal. Let's keep going. This looks a little clunky and crazy, sorry. Let's talk about some statements though. So if the point P is the lowest point, then P must be a global minimum. that is true. That's kind of just a definition thing. If it's the lowest point on a graph, then that must be the global or absolute minimum. Number 2, a local max is a point where no nearby points are higher. Okay. So local max is a point where no nearby points are higher, meaning the nearby points are lower, which is true. Holy cannoli, sorry. You know what, I'll just leave that there. So that is a true statement. That was, oh shoot, crab apples. All right. So number 2, yeah, local max is a point where no nearby points are higher. That is true. That's a local max. Good night. I hate my hair. Holy crap. All right. Sorry. F is differentiable. First derivative changes from negative to positive at a local minimum. We saw that before. That is true. F prime changing from negative to positive means the slope changes from negative to positive, so we do have a minimum. If the point P is the highest point, then F must be the global max. That's exactly right. Highest point means global max. Number 5, if F is differentiable, changes from rising to falling, then F has a local minimum. So close, but just the opposite. F would have a local maximum. So that is the only false one. I think 1 through 4 are correct, and I think that is B. All right, we nailed it. That's all I have for you today. I don't even know what number we called that. Oh, it's number 18. Look at that. So that could be a whole exam if the whole exam was on quiz 9 here. Lots of problems, lots of good stuff today. Hope this all made sense. Did a lot of stuff in Excel. I definitely suggest you learning how to do those in Excel. Unless you want a challenge and want to learn how to do it by hand, I promise you it's harder by hand. It's definitely worth using Excel. If Excel is not your strong suit, it's still worth learning it. I very much encourage you to do so, but hey, if you want to work it out by hand, I do have videos, I'm pretty sure, which work out all these problems by hand as well. So feel free to check those out. I'm just kind of scrolling backwards through all these problems. There's not a lot of work for these, apart from the earlier ones. I think even, I don't know though, this was Excel. That was also a little bit of Excel. That was a little bit by hand. A little bit by hand. A little by hand. Definitely by hand. As well as the first one. By hand. But I'll be honest, you could do these in Excel as well. I'll leave it at that. Thanks so much for watching. It's about 5 o'clock. Finished up in less than an hour. A lot of good stuff in this video. If you have questions about anything, please let me know. Next week will be, I guess, the exam 4 review, last midterm exam of the semester. That's fun. Okay. Yeah, if you have specific questions you want to see me work out in that video, you let me know. All right. I'll see you next time. Bye-bye. Thanks for watching.